This is Lesson 9 for AP Calculus, Limits and Continuity. We're going to be looking at a particular function or different functions and how they react at a particular value for x. So we're looking at continuity as x equals some particular value. Here's a function that we have, and we're going to be comparing the limit of the function as x approaches 3 as well as the value of the function at 3. And we notice that in both cases, both the limit and the value of the function are 8. In this other function, we can look for the limit at 3 and the function at 3. Remember, the limit is looking at the left hand as it approaches 3, as x's are approaching 3, what is happening to the output, as well as the right hand side as it is at the x's are getting closer to 3, what is the output approaching. And we notice that both of the limit and the actual function are the same value. In this third function, we can look at the limit as x is approaching 3 from the left and the limit as x is approaching 3 from the right. In both cases, the limit approaches -2. And the function itself is, the value of the function at 3 is also -2. So we've got both the limit and the value of the function are equal. This is the definition of a function being continuous at a particular value for x. So a function is continuous at x equals c if the limit as x is approaching that c of the function is equal to the value of the function evaluated at that c. Now, discontinuity, instead of continuity, discontinuity, we have 3 different types. So when we're looking again at a particular place, not the entire function, but at a particular place on the function. And the first one would be a point of discontinuity. And it appears in the graph as a hole. It's called a removable point of discontinuity because it's as if something was just removed from the function itself. So here is here's a picture of one function that has a point discontinuity, and we can see right here that that there's a hole in the middle of this graph. Now, the value has been moved here. We don't even have to have that. If we just had the hole, that would be a point of discontinuity. But in fact, this one does have a value at f of 2, but it is not on this continuous function anymore. So it's not. It is discontinuous and it has a point discontinuity. And what we say is that the limit as x approaches 2, which is 3, we can see that the left-hand limit and the right-hand limit at 2 is 3, but the function itself evaluated at 2 is not 3. So since they do not equal each other, then the limit does exist, but it does not equal the value at that c, and that is called a point discontinuity. So this is the definition of point discontinuity. Another type of discontinuity is called jump discontinuity, and it is not removable. It's actually where part of the function is in one place and then it actually like jumps to a new location and then goes on from there, and that's called jump discontinuity. So this is a graphic picture of a jump discontinuity, and what we say there is that the limit doesn't exist. And the reason the limit doesn't exist is because in this particular case, the left-hand limit at 2 is -2, but the right-hand limit at 2 is 4. And since the left-hand limit and the right-hand limit do not equal the same amount, the limit does not exist. So a jump discontinuity would have a limit that does not exist. Again, we look at the left-hand side and the right-hand side, they are not equal. So what is the definition of jump discontinuity? Well, exactly what I was saying before, when the left-hand limit does not equal the right-hand limit. And so that is jump discontinuity. The third type of discontinuity is called infinite discontinuity. And here's, it's not removable again, it doesn't have a hole or something in it, it's different. So this is a picture of a type of infinite discontinuity, and you'll see that at x equals 2 we have an asymptote. And on the left-hand side, it is growing as x approaches 2. It is growing and growing, and it'll go towards infinity. On the right-hand side, as x is approaching 2 from the right-hand side, it also is growing to positive infinity. They both have to be going to the same direction, but they will never connect. They will never come across this asymptote, and it will never connect. And therefore, because of that, the limit does exist. The limit is infinity, that it's positive infinity, because both sides are growing without bound. But the function itself does not exist at that place. Now, infinite discontinuity would be when the limit is either positive infinity or the limit is negative infinity. You can't have one side the limit going up and the other side the limit going down, because then the limit would not exist. The third part of our lesson today is about piecewise functions. So, piecewise functions. Here is an example of a piecewise function. It's one function that it's made up of other subfunctions. And it could be 2 or 3 or even more. It could have many, many different subfunctions. In this case, we just have 3. When our values for our input are less than -2, this function will just return a 4. The output will be 4. When our inputs are between -2 and +2, including both of those, we will just square our inputs. When our inputs are greater than but not equal to the number 2, we will negate them and then add 6. We will follow this rule here. So this is the piecewise function for f of x. We're going to look at continuity of a piecewise function. What we're interested in is these areas where it links one subfunction to another. So we're looking at these transition places. For when x is -2, it would go from this particular definition of f of x to the x squared. So from going from the definition of the function being just the number 4 to the definition of the function being the squaring function. That transition happens at x equals -2. And similarly, it transitions from the squaring function to this linear function at +2. So we want to look at the continuity at those particular places. So we're going to look at, numerically, the limit of this function as x approaches -2 from the left. This little negative means from the left. So I'm thinking about inputs that are less than -2. Well, if it was less than -2, I'm going to use this definition, which means anything that is to the left of -2 will return a 4. So I know that that output would be 4. The next limit is looking at the limit as x is approaching -2 from the right. To be approaching from the right would mean the inputs are greater than -2, but really close to -2. So we would be in this group right here, and that would mean we would square it. So as it approaches -2 from the right, we would be squaring it, which would mean we'd be squaring -2, which would give us a 4. Well, since our left-hand limit and our right-hand limit are equal, and that also happens to be in this piecewise function, when you plug in -2, you have the answer of 4. That means the limit and the function value itself are equal, which means it's continuous. That's the definition of continuity at that point. We have to look at the other transition, which is at x equals 2. So we're going to look at the limit from the left, and that's 4, and the limit from the right, and that's also 4. And since that is also the function at 2, because we would plug in a 2 and we'd be using the squaring function, we can see that the limit is 4 and the value is 4. So therefore it's also continuous at x equals 2. Now, it's a little bit strange because it looks like, well, gee, then aren't all the limits just 4? And no, it just happens to be at these transition places that's true. So we need to also look at this graphically. Just looking at it numerically is not enough right now. We need to do it numerically and graphically. So we need to graph this piecewise function. Well, here's the graph of the piecewise function. For all of the inputs of -2 or less, we just return 4. So we have that horizontal line. Between -2 and +2, we have the parabola x squared. And from +2 and greater, we have this line, which is -x plus 6. So this is a picture of it, and we can see now graphically that there's continuity here. There's no hole, there's no jump. It is just a nice smooth transition from one function to the other with everything filled in. Let's look at another piecewise function. And it just so happens I ended up picking the same transition points. We've got the transition point of -2, and we have another transition point at 2. So we need to look at where the limits at -2 and the limits at 2. And remember, I'm saying limits plural because we need to look at the left-hand limit and the right-hand limit. So starting off with the -2, I'm looking at the limit of -2 from the left. Well, I would be using this top function here, which would be 5. So I'm going to put in a 5. And from -2 from the right, well, I would be using this middle function because I'd be in here. And I'm going to square it. Well, -2 squared is 4. Well, 5 and 4 are not equal. Since the left-hand limit and the right-hand limit don't equal each other, the limit does not exist. And we would do the same thing with the other transition, this x equals 2, to check for continuity and find out the same thing, that the limit does not exist. Since that's the case, we need to look at this graphically. So you're going to graph the horizontal line 5, you're going to graph the parabola, and you're going to graph this linear function, -x plus 4, in their appropriate domains. And we have this function, and you'll notice that there happens to be a jump discontinuity here and another jump discontinuity here. We knew that it would be jump because the limit does not exist. So what I want you to do is I want you to do this problem. I will leave the answers with the sub for you to check. So I have a piecewise function, and I want to know if it is continuous at 3, because that is the transition point for this particular piecewise function. When it goes from one of the sub-functions to the other is at 3. So I want you to check for continuity, and I make sure you are checking first numerically, and then after you've checked for the continuity numerically, then graph the piecewise function to double check your results. When you're done with this and you've checked with the answers with each other and with the sub, then move on to doing your homework for tonight.